Right, okay, hi everyone. I'm going to make a start now on our afternoon session on motion graphs. I'm going to work today on graphs in general and also some of the maths behind graphs. But we're going to start off with a focus on motion graphs and what you can interpret from them. This is largely sort of born out of what I've seen in some of the feedback I've received, where I think we can cope with things like Suvat equations, no problem, which to me are kind of one of the harder bits of kinematics. But when it comes to interpreting graphs of motion, it's quite a difficult one for some people to sort of grasp. So I'm going to talk you through two basic types of motion graph. The first one I'm going to talk to you about, and do be aware, of course, as per usual, I am recording, just so that you're aware. So the first one is what we call a displacement time graph, very similar to a distance time graph, and certainly at UFP level, we generally interchange between the two pretty seamlessly. So a displacement time graph is literally a graph of displacement on the y-axis, also known as distance, versus the time taken. And I'm going to show you a few different examples, and then we'll sort of look at the actual physics behind it. But the whole point is if you've got a graph that's displacement, which we call S in meters, time t in seconds, the simplest way to look at a displacement time graph is to look at how we represent motion with it. So, for example, if I have a displacement time graph, the key is that the gradient equals, it's the same thing as its velocity. If you think about it, the velocity of an object, its definition, is the rate of change of velocity. Velocity is the rate of change of displacement over time. So displacement time graph's gradient gives you the velocity. So that to go for the very, very most simple, which I'm going to do in blue, is if I have a displacement time graph which looks something like that, okay, then that's going to be constant velocity. Okay, so if I look at one that's in a particular sort of state here, the A is constant velocity. And because it's a positive gradient, it's forwards, okay? We refer to it as being forwards. Just admitting the last few people. So that part would be a constant velocity. Now, the other part that people get very confused with the displacement time graphs is where the gradient gives you the velocity. So the whole idea behind these is if you remember that and then apply that knowledge, then it becomes very, very simple. So if we take that particular part there, where it's horizontal, it basically means that something's stopped or stationary. Okay. If we want to change a graph, if we have a graph that looks something like that, if we think about it, we just use this basic bit of logic, gradient is velocity. Well, here the gradient is increasing from 0 to a higher value. So therefore the velocity is increasing from 0 to a higher value. In other words, it's accelerating. Okay. If we then take another part where we do almost exactly the same thing, but this time on this part in section D, the gradient's decreasing. As the gradient is velocity, the velocity is decreasing. What's that? Well, that's a deceleration. Okay. Now, if I was to then take a graph and take my distance time graph and make it like that, against a straight line, so it's constant, okay, so it's constant velocity, but you notice the gradient here is negative. If the gradient is negative and the gradient is velocity, then velocity is negative. So what does a negative velocity mean? Well, a negative velocity actually means going backwards, okay? Okay, so you can plot quite happily what's going on in terms of the motion of an object using a displacement time graph. So one particular example might be a very short car journey. Let's say somebody does a 30-second car journey. So if we plotted displacement time graph for that, we could actually start putting in various values. We could start sort of using estimated values. And as we said before, estimation is very, very useful because you can apply your physics without knowing actual, without knowing numbers off by heart, then there's no approximate numbers. So that's displacement in meters or distance in meters. It could be the same thing really. Remember, displacement is just distance in a particular direction. There's your time in seconds. Let's say for the first 10 seconds, the car starts from 0. So remember, gradient of a graph is negative. Sorry, the gradient of a graph is velocity. So the gradient will start off at 0 and the car will increase in velocity until it's covered a distance, let's say of 100 meters, let's say. So actually 100 meters in 10 seconds, that's pretty swift, but never mind. So start off at 0 and the gradient increases. So you've got your curve there. So that's the car accelerating. Now, if it then continues at the same speed, you're not going to get a kink in the graph, same gradient, but this time at a constant speed. Okay. And let's say it continues for, let's say it continues for another 20 seconds. So it's 30 seconds. And well, let's say it's traveled, I reckon that'll be about 400 meters. Okay. And then the car hits the brakes. Now, if it hits the brakes, the velocity is going to decrease, so the gradient of your graph decreases. There we are. And let's say it does that in 5 seconds or something like that. Just pulling numbers out of thin air, really. That should be a dotted line, I apologise. So there's 500 meters. So the car's total journey length of journey was 500 meters. And you could see it started at stationary. It increased in velocity, so it accelerated. We don't know if that's a constant rate. It's not easy to tell. It's not easy to tell from the graph, from a displacement time graph. But here we see we've got a straight line, so we've got a constant velocity. Then it decelerated because the gradient's getting less until it stopped. So if you want to work out the speed at any given time, it's literally the gradient. Well, here we've got our y1 and y2 values. So here, the velocity, well, it's distance traveled over time taken, or the gradient of a displacement time graph. So the velocity would be delta y, which is 400 minus 100. So that's 300. Divided by the time taken, which is 20 seconds. So the velocity would be, well, it'd be 15 meters per second. Easy as that. Okay. So that's how you calculate the velocity. It's the gradient. It's not that difficult. I think the thing that people get very confused with, they mix these up with my next sort of part of my lesson, which is velocity time graphs. Okay. Now with velocity time graphs, again, there are 2 rules here to know, okay? Now these rules actually make the most sense if you've ever studied calculus. if you've got a velocity time graph, then the gradient is equal to the acceleration, okay? And the area under the graph is actually your displacement. Okay, so if we look at a particular sort of style of motion, let's say, okay, if I look at my original displacement time graph, I could draw an equivalent velocity time graph. So here I've got my constant velocity. So I started out at a constant velocity. There it is. So because my velocity is constant, then it's not going to change. So that y value of velocity is going to be exactly the same. It's going to stay the same. So it's got a horizontal line to start off with. Now with B, you see it stopped. Okay, so there's B, exactly the same motion. With part C, we're accelerating, so velocity is increasing over time. So it's doing, I'm going to exaggerate it slightly there. So part C there. Okay. For part D, remember the gradient here is decreasing, so the velocity is decreasing. So it's decelerating, which is a negative acceleration. Okay. And then part E shows a constant velocity, but negative. So I think it's getting a little bit silly here. It'd be something like that. Okay. So you can represent motion quite happily with a velocity time graph, but you just got to remember that whatever the velocity time graph has on its as its shape, it's the gradient of a displacement time graph. These two graphs represent the same journey. Now, the thing that we notice here is that here we've got we're told the gradient is the acceleration. Here, the gradient here is massive. It's really big because it's infinite. Okay, delta y is a number, delta x, the time taken, is 0. Where anything divided by 0 is infinity. So this would imply an infinite acceleration, which is why if you were drawing a displacement time graph, in reality, you wouldn't have these sort of kinks. These corners would be rounded off. Okay, which makes sense, really. Remember, in physics, we very rarely get sort of sudden changes in the gradient of a graph. Now, if I was to use so that's qualitatively. If I now used the same bit of science, but I worked out my velocity time graph for this distance time graph, I would need to use some actual numbers. Okay, so my time axis would be exactly the same as it was before. And I'm just going to tidy up my example here, so I just want to make sure that you've got my example in front of you while I'm showing you the equivalent velocity time graph. So if I drew the equivalent velocity time graph, I'm just going to zoom out a tiny bit so we can get some. There we are. If I drew exactly the same time axis, because that makes sense, that's 35. Okay, there we are, on there, on there. But this time we did velocity in meters per second versus time. I put on my 10, my 30, and my 35. I could actually work out what I'm doing here. Here, we said we're accelerating. Now, if we accelerate, if we remember, we're not going to get sudden kinks. So this gradient here is going to be probably pretty much the same as here. So we're accelerating to 15 meters per second. Okay, so if I was to draw my graph, my velocity time graph for exactly the same motion, assuming that we've got constant velocity, constant acceleration, I do apologize, or uniform acceleration, would look like that, the first 10 seconds. The next 20 seconds, here I've got a constant velocity of 15 meters per second. I worked it out before. So if I draw my line up, say from here to here, and then I decrease my velocity from 15 meters per second here to 0 over here. Again, I'm going to assume it's a uniform rate. In foundation level exams, nearly always the acceleration is uniform. There we are. So that's your base. Those are the basics of graph drawings. But then we can actually do our calculations. Well, you can work out here the acceleration is the gradient of the graph. So the gradient is delta y. Well, we started off at 0, went up to 15. So that's 15 over 10, which is 1.5 meters per second squared. It's 1 point because that's the formula for acceleration. One of the things I've learned from your feedback is that most of you are pretty good at actually doing the calculations. It's just this visual bit that people are struggling with. So here we've got acceleration. Again, it's a gradient, but this time we're going from 15 down to 0. So it's 0 minus 15. Because it's deceleration, and that's in 5 seconds. So that's minus 3, whoops, I do apologize. There we are, meters per second squared. Okay, so you can calculate the acceleration from the velocity time graph. Now, we can also calculate the total distance traveled. Now, according to my calculation, I had said that it traveled 500 meters. That was my estimate. Let's see if it actually works. I'm not sure if this will actually work, but because I just drew this from my own imagination, really. So work out the area of this. We can actually work out the area of a trapezium. This is a trapezium, okay? So the area here find a different pen, use green. Okay, work out the area of that trapezium. We know the area is the displacement. Remember, use S in Suvat equations for displacement. So the trapezium rule says that we've got a height of 15 multiplied by, well, it's the average width. So it's going to be 35 plus 20 divided by 2. Okay, and you can work that out. Well, okay, let's get our calculators out and see if it works. It should be in the region of 500, but just want to be certain. 15 times 30, 35 plus 20, close brackets, divided by 2. There we go, 412. Well, it's in the right sort of ballpark, isn't it? Okay. So we can see exactly how far something has actually traveled. We can, you can actually see that it makes, you can actually interpret the graphs. As I say, from what I see, for the most part, you're pretty confident with the math side of things. The thing to remember is actually, for those of you who are really into your maths, the thing to remember that that the velocity at any particular time is the rate of change of displacement with respect to time, which is the gradient of the graph. And we know the acceleration is the rate of change of velocity with respect to time. Okay. Now it stands to reason when you think about it, a lot of people get very confused about this area under the graph business. So if we look at the area under a graph, well, the area of the graph under a velocity time graph is going to give you is going to give you the distance traveled. And there's a reason for it. And that's that if the velocity is the rate of change of distance with respect to time, then the distance would be the reverse of this, which, if those of you do calculus, you know that that's going to be the area under the graph integrated with respect to time. Pretty simple. It should be T, not V. I do apologise. There we are. Okay. So that explains exactly why the graphs behave that particular way. Now, the bit that I think we just need to really sort of work on is interpreting them. So there are two particular types, or rather three particular types. It's 2.5 really, of velocity and distance time graph that you'll come across in your in exams at your level. The first one is free fall. Now, if we think about it, if I was to draw side by side my velocity time graph and my displacement time graph side by side, I can actually start to demonstrate what I mean by interpretation. So if I draw a velocity time graph for free fall, obviously everything falling under gravity, if there's no air resistance, it will have a constant acceleration. So if we have no air resistance, we would have a graph that looks something like that. But what actually happens in the real world is that things accelerate at the beginning when there's very little air resistance. The faster you go, the more air resistance there is. So at the beginning of a free fall, an object will accelerate at a constant rate. Now, as it starts to accelerate, we know that its speed through the air is greater, which means that the drag forces due to air resistance are also greater. This means that the net force on the free falling object is going to be less because there's going to be more counterforce from the air resistance. If the net force is less, force is proportional to acceleration if the mass is constant. So that means that the force is proportional to acceleration, which means the acceleration becomes less. So the gradient of your velocity time graph becomes less until eventually you get to a point where the velocity is constant. And that's what we call, for an object free falling, that's what we call the terminal velocity. Now, in the when we talk about free fall, we can actually apply this to a lot of other things where there are resistive forces, particularly air resistance. Because if you've got a car or an aeroplane or a rocket or a helicopter or any other example we've used in our 6 so far practice exams, you probably find that they use the same physics. The idea that as the speed increases, the drag forces will also increase. So the net force on the object, whatever it is, will therefore decrease. The acceleration decreases until such a time as the acceleration becomes 0 because the forces are balanced. So it's a weird thing. People can get very, very confused by the idea of something moving being in equilibrium, but technically it is in equilibrium. A free falling skydiver at terminal velocity is in equilibrium. The forces are actually balanced. It's just the fact it's moving with a constant velocity. So if we were to translate that into a displacement time graph, remember S is displacement, then we can start to we start to use a little bit of logic. We have to use our brains a little bit. So what do we get here? Well, we get the idea that first of all, the velocity is 0. And then it is the skydiver is accelerating. So we could represent that acceleration starting with a 0 gradient and increasing over time. Until eventually, that rate of acceleration is still accelerating here. So the gradient's still increasing. Until we get to here. And it's gradual. Look how gradual it is. No kinks, no corners. We end up with a constant gradient here. And that gradient then gives you, that tells you you've got constant velocity, which is here. So I could separate this into A, B, and C. A would be this initial bit with quite a rapid acceleration, so it's rapidly increasing gradient. The rate of increase of gradient sort of gets a bit slower over time, so it's B, until eventually you get a constant gradient, uniform velocity, it's C. So those two are the same graph. So that's obviously with air resistance. Now, without air resistance, we would just have a constantly increasing gradient. So A would be exactly the same, but we start to get a departure and bear with me. Find a pen that works. I'm rapidly losing pens that work. Here we go, try again. So we'll get a rapidly increasing gradient, and the gradient would continue to increase parabolic in a parabola. Okay, so that would be if there was no air. Okay, it would never become a straight line. It would always be increasing in gradient at the same rate. Now, if we ignore air resistance, we often saw an example that came up in an exam today, which I think many of you struggled with, is the idea about a bouncing ball. And we're just going to concentrate really on the velocity time graph, because it was the interpretation of that seemed to give a lot of people confusion. Now, whenever you get a direction question, a question whereby things change direction, you've got to start thinking a bit in terms of vectors and defining one direction to be positive and the opposite direction to be negative. So here in a bouncing ball, I'm going to say that downwards is positive. Okay. So if you've got a bouncing ball, well, the first thing that happens is the ball's dropped from a certain height. In fact, I will do the displacement time graph and the velocity time graph next to each other with this, because I think it actually helps you to make more sense about it. There we are. Changed my mind ever so slightly. So if we think about it, if you've got a bouncing ball, it's being dropped, starts to be dropped from a maximum height, okay? At some point, it will move downwards. Well, if we're saying that down is positive, actually, if we're lifting something up, its initial height is going to be negative. Now, in time, we know that the ball, while it's being dropped, will accelerate. So the gradient will increase from 0 up to a certain value. Okay, and then obviously it'll bounce. So as it bounces, it will decelerate upwards. So its gradient will decrease until eventually it has leveled off, and then it's moving back down again. So it's a positive gradient, and so on. Okay, so that would be the displacement time graph for somebody bouncing a ball. if we said down was positive. Obviously, if we said that up was positive, then this would be the other way up. So then we think about the gradient. Well, we know that everything that accelerates due to gravity, if we ignore air resistance, will accelerate at 9.81 meters per second squared, or roughly 10. So if we're ignoring air resistance, this will be a constant acceleration until we actually reach the ground, okay? So it starts off at 0 because the gradient's 0. It's a positive gradient, so it's going to go up. So what will happen in time is you'll get a constant acceleration. So there the ball is falling, okay? Its downwards velocity is increasing. Now it's going to hit the ground, and it's going to then have a negative velocity because we've got a negative gradient here. So here, at this point, it's going to be changing direction very suddenly, because here it's moving down, here it's moving up. Okay, because it's bounced. It's changing from moving downwards to bouncing and moving back upwards. It will move up a certain distance. Now it will accelerate at the same rate as it did before because it's still under Earth's gravity. At this point, it's still moving upwards, but its velocity is decreasing and decreasing until eventually the velocity becomes 0. The natural thing for it to continue doing, though, is to continue moving, but this time it's going to be moving downwards. Okay, so eventually it will then hit the deck. I've not drawn this terribly well. Very, very sudden change in direction. And then again, we've got another, because it moves to a positive gradient, and then move to a negative gradient, so it's negative velocity, and so on. So what's actually happening with the bouncing ball here is on this part it's falling. Bounce, it's sudden change in velocity. If you think about it, it makes sense that there's a massive acceleration at that particular time. Going up at that point, then falling again, and so on. Okay, so that is roughly the sort of the motion graph, something like a bouncing ball. It's all about interpretation. In terms of actual motion, just to remind those of you, because one or two of you have said you need a little bit of a reminder about Suvat equations, you just have to remember the key Suvat equations. We call them Suvat because we always write Suvat. It's always cases where you get a constant acceleration. Okay? If you get a constant acceleration, then you can apply Suvat equations. If it's constant velocity, you're just using velocity as displacement over time, or speed as distance over time. The thing with the Suvat equations is there are 4 of them. We know that velocity is final velocity is initial velocity plus acceleration times time. We know that distance displacement is ut plus a half at squared. We know that displacement is also the average velocity. If it's constant acceleration, it's the average velocity over 2. So it's the velocity, it's the initial velocity plus the final velocity over 2 multiplied by time. And we also know that we've got the final velocity squared is initial velocity squared plus 2 times the acceleration times the distance. Okay. These 2 are on your formula sheet in your exam. These two you have to remember. The way I remember it is the obvious one is accelerate. If this one stems very obviously from acceleration, is the change in speed or change in velocity divided by time, which is basically the final velocity minus the initial velocity over time is equal to A. I rearrange it to make V the subject. And then we can, you just rearrange it to make the velocity of the subject, the final velocity of the subject, and you end up with that one. This one's easy because that U plus V over 2 is actually the average velocity. The initial velocity plus the final velocity over 2. If you think about it, it's an average, isn't it? You're taking two velocities and adding them together and then dividing by 2. So if distance traveled is velocity times time, then it's going to be average velocity times time. Right, just a quick question. I've just been asked, can I show the other sheet to finish writing something? Do you mean that one?
Yes, Gary, thank you.
Okay. Well, while that's there, and I'll let you continue writing, we've got about 5 minutes left. I'm going to talk to you about where we're going to go from here. Obviously, if there are areas you're struggling with, please let me know. I know that I was told the other day by a couple of people that it was actually interpreting the velocity time graphs that people have trouble with. The other thing that I think that people have said they're having a lot of trouble with at the moment still is to do with uncertainties. If there are other areas you want me to have a look at for you and to sort of go over again, this is a good time. This is a good time to ask about it. The other thing, that's no problem. The other thing I just want to point out to you is that tomorrow, again, you've got another practice exam. Now, I know it's a lot of practices, but the practices do seem to help you to make progress. So I put a bit of thought into this one, the one that you've got, which you'll be able to download tomorrow morning. I want you to go through it, and then by the end of this week, please just email me, hand in whatever you've got, whatever you've come up with, just hand it in to me and I'll have a look at it. I have put a bit of thought into this one, bearing in mind that many of you have said you're finding a little difficulty with the kinematic side of things, particularly with things like using Suvat equations, although you're better at that nowadays, and also just sort of interpreting graphs. I have selected, or rather written, some questions which are tailored towards that to give you a bit more to think about. In fact, you'll find particularly the question 2 in tomorrow's paper is quite challenging. The trick is really to think about which direction you're regarding as positive and which direction you're regarding as negative, because that's, I think, one of the little areas that we just need a little bit more practice on. So that's your task for tomorrow's lesson. I'll be around, so you can email me if there are any problems. You want, you want a bit of extra help on something, you want to ask me something, not a problem. Just ask. Just like Hogwarts, help comes to those who ask for it. If you want to, if you want to ask me anything, please do. But have a go at doing that particular paper and give it your best shot. I think it is harder than average, but I think that's what makes it worth it. For those of you with the papers you did yesterday, I've now marked them. I will scan them this afternoon and I'll send them in to you as soon as I can. I've got a pile of admin to do, but I should be able to hand those papers, to scan those in for you and give you your feedback. Okay. Any questions? Well, I'll take that as a no. I will see you all. Well, I mean, do keep in touch. But the very latest, I will. We'll have another lesson on Tuesday. So you've got your lesson tomorrow, which is really another practice paper that I want you to have a plough through, please.